Hey everyone, welcome back to our Calculus 3 class notes. We are now on page 64 and we're still in section 14.6, and now we're talking about how to use differentials, just much like we did way back in Calc 1 where if you remember, dy equals f prime of x dx, so that would be estimating the change delta y by following the tangent line instead of following the curve. So we're going to do the same thing here. If we want to estimate the change in the value of a differentiable function f when we move a small distance ds from a point p naught in a particular direction u, then we use this formula. So what we have is this is the directional derivative, right, in the direction of u. So we're going to follow that line or follow that slope, and then we're going to approximate the change in f, which would be delta f, with df, which is follow the tangent line a certain distance ds to approximate df, to approximate the change in f delta f by this differential df. Okay, so for example, in example 59, estimate how much the value of f of x, y, z equals y sine x plus 2yz will change if the point P, x, y, z moves 0.1 units from P naught, 0, 1, 0, straight toward P1, which is 2, 2, minus 2. Okay, so what's the direction? Well, the direction that we're moving here is the vector P naught to P1, but I want to make it a unit vector, so I'll divide it by its length. So the vector P naught to P1 is 2 minus 0 is 2, 2 minus 1 is 1, and minus 2 minus 0 is minus 2. So it's clearly not a unit vector. We'll make it a unit vector by dividing it by its length. So when I divide it by its length, now the direction that we're following the tangent line is 2/3, 1/3, and minus 2/3. Okay, so I take the gradient of f and I evaluate it at the point where we're moving from, and I get 1, 0, 2. Now the gradient of f dotted with u will give me the slope of the tangent line right at that point, 0, 1, 0. So the function will change a certain amount from this point to this point. But I'm going to approximate. So instead of doing f of 2, 2, minus 2 minus f of 0, 1, 0, that would be delta f, right? The actual change in the function. I want to approximate it with df, which is just take the directional derivative, which is minus 2/3, and multiply it times the distance we're going to move along that line, which is 0.1. And so the approximate change in f will be about negative 0.067 units. Okay, similarly, we can do the linearization of a function. Instead of following the tangent line, we're going to follow the tangent plane. So linearization of a function f of x, y at a point, x naught, y naught, where f is differentiable, is given by the following. So in other words, what we're doing is we're taking a function and we're approximating that function with its tangent plane, now only close to where it touches, but that's important to always think about. But we're going to approximate the function f of x, y with the equation of its tangent plane. So why is this using the equation of the tangent plane? Because this is the tangent plane right here. Remember, we take the gradient of f, evaluate it at x naught, y naught. So we take the partial of f with respect to x, evaluate x naught, y naught times x minus x naught, plus the partial of f with respect to y times x of x naught, y naught, evaluate times y minus y naught. And then minus, this coefficient is always 1, times z minus z naught equals 0. So if I solve this for z, which is f of x, y, that then will give me an approximation to f of x, y, because this is the plane. So it's not the function f of x, y exactly, but it's certainly close to where this tangent plane touches the surface. This will be a decent approximation of the surface near x naught, y naught. So for example, let's say we want to find the linearization of this function, f of x, y equals x squared minus xy plus 1/2 y squared plus 3 at the point 3, 2. That just means we want to find essentially the equation of the tangent plane at that point 3, 2. Okay, and then that will be the linearization of the function. Again, I'm solving for z here, but just remember it's always going to be this formula here. Okay, so it's the function f at x naught, y naught, right, which is 8 in this case. Evaluate f at 3, 2, I get 8. Then I have to take the gradient of f, 2x minus y, minus x plus y. Evaluate that at 3, 2, get 4 minus 1. So I have 8 plus f sub x, which is 4, times x minus x naught, x minus 3, plus f sub y, which is minus 1, times y minus y naught. So this is the linearization. This is if I was following the tangent plane instead of the function. So I can approximate any point on the surface, f of x, y, that is near the point 3, 2, with plugging it into the equation of the tangent plane here.